So elliptic. So there's three things. There's something called elliptic curves. Elliptic curves. There's something called elliptic integrals. And something called elliptic functions. And none of these have anything to do with ellipses. Well, that's not true. It's not entirely true. What do they have to do with ellipses? It's a little, so it's funny, you open up any modern book and they're like, you know, Legendre did a bunch of stuff and Euler did a bunch of stuff, and then Jacobi and Abel came in, and then it was all kind of lame, and now we're just going to do the modern Weierstrass theory. And Stein too, you know how much I love Stein, but Stein too, you opened it up and it's like, there's this old-fashioned stuff, and then now we're going to do the modern stuff. I don't know, maybe I'm old-fashioned, but I'm like, where would you even get these ideas from? So I want to show you some of the prehistory and where these ideas come from. So, all right, so let's back it up just a little bit. So what is an elliptic curve? By an elliptic curve, people usually would write something like y squared is equal to x cubed plus ax plus b. So this is, standard form of an elliptic curve. It's a curve. It's a quadratic equation in y, a cubic equation in x. In this standard form, there are lots of other versions of things that can be called elliptic curves. A typical, there's a curve. It's some equation. A typical elliptic curve looks like this. If I just plot the real points of an elliptic curve. So it has this word elliptic in it. It has nothing to do with ellipses. Doesn't look like an ellipse. So why? Why do people care about these things? So if we go back, way back, so if this wasn't a cube, if it was a square, does anybody know what quadratic curves are? Quadratic curves like some coefficient ax squared plus, let's get as many x's as we can, keeping the degree as high as possible. So now that's all I can do with x's. What can I do with y's? I can do y squared. I've already used xy, so now I have a y, and then I think that's it. And now I have a constant equals 0. Okay, so that's the biggest, that's like the most general possible thing you could write down with quadratic, with at most degree 2. No homogeneity, nothing, just it's a curve. So it's an x and a y. And when I put this equal to 0, it's going to be some shape. Some shape, I don't know, I have no idea what it is. It's some one-dimensional shape in the two plane. We have an x and a y, and there's an equal sign, which means, if there are any points satisfying this, it's going to be a line, a curve. Does anybody know what kind of curves you'll see? Okay, so this is the classification of conic sections. So it turns out that all such curves, it turns out, is very easy to understand geometrically. They are conic sections. So what does that mean? Conic sections are sections of a cone. So you take a cone and you slice it by a plane. And it turns out that when you slice a cone by a plane, the intersection, whatever this intersection is what's called a conic section. And it turns out, and this is due to Apollonius, by the way. So Apollonius worked all of this out in like 250 BC or whatever. Apollonius works out that you'll only get three core types of possible curves. And the core types of curves, does anybody know what now that I told you conic sections, do you know what the classification of conic sections is, Kaylee? Yep, ellipse. Let's get the first couple. Ellipse, exactly right. Ellipse, hyperbola. And the last one, so hyperbola is more than the bola, and parabola is parallel, the same as the parabola. Right. So, and he, by the way, invented these words. Apollonius coined these terms to exactly describe what happens. So if you cut the plane, let's see, can I zoom in on here? If you cut on, what's going on? I want this color. Yeah? No? Please? Yeah, okay. I have to ask nicely. If you cut on a plane that's still less slope than the slope of the cone itself, you get an ellipse. If you cut on, I don't know, if you cut exactly along the same slope as the slope of the cone itself, then you get a parabola, parallel bola. And if you cut it at a sharper angle, whatever, is there any other nice looking color? And if you cut at a sharper angle, you'll get a hyperbola. And by the way, the cone continues down here, and you get the other half of the hyperbola down there as you slice through that. Okay, so he proves these things, and in fact, all of these. So a typical ellipse is like x squared plus y squared equals 1. Well, that would be just a circle, but up to scaling, I can put a parameter like k here. You know, people often write x squared over a squared plus y squared over b squared, where a and b are the major and minor axes. A hyperbola would be like x squared minus y squared equals 1, or x times y equals 1. And a parabola, okay, is like y equals x squared. So we know what these of course they didn't this is all attaching shapes, geometric shapes, to algebraic relations is Descartes, right? That requires the Cartesian plane to say we're going to plot all the pairs of points that satisfy these things. But okay, fine. We're going to jump back and forth. We're not trying to do something totally historically. Do we know how to parametrize these kinds of equations? So, in other words, you could just say, well, I want all points that satisfy this equation, but do we actually have a way of having one parameter that then explains what it's a curve? So there should be one parameter that allows you to trace through the curve, right? In the case of the ellipse, so what is this ellipse going to have? X is going to go, if y equals 0, then x is plus or minus k. So this is k and minus k. And if x is equal to 0, then y is plus or minus 1, the way I've normalized it. Okay, so there's our ellipse, whatever k is. And so can we parametrize an ellipse? You guys know how to parametrize an ellipse? Well, what if it was a circle? How do you parametrize a circle?
There's sine of t and sine of t.
Perfect. So if I square this, I'll get cosine squared. If I square that, I get sine squared. I don't want the sum of those to be 1. I want 1 over k squared times x. So if I put a k here, then when I square this, I get a k squared. When I put a 1 over k squared in front of that, I get back to cosine squared plus sine squared is 1. Okay, so this is a parametrization. So these transcendental functions, cosine and sine, and we have this parameter implicit in front of everything that we're just thinking of as fixed. These are transcendental functions, but functions that we're very used to, transcendental functions parametrizing an ellipse. Okay, how do we parametrize a hyperbola? Or a hyperbola like x squared minus y squared equals 1. Of course, we could add a parameter here, but never mind. It's already fun enough as is. Do we know how to parametrize hyperbolas? We didn't discuss this when we discussed hyperbolic sines and cosines. That's exactly what hyperbolic sines and cosines do, right? If I put cosh t and sinh t, cosh squared minus sinh squared is 1. Right? So again, these are transcendental functions that parametrize the hyperbola. How do you parametrize a parabola? It's already parametrized. X is equal to x and y is equal to x squared. So it's very easy. You don't even think about parametrizing a parabola. But for the hyperbola and ellipse, which are sort of generic, right? If you just take a random cut without even thinking through a cone, the chances that you'll cut it parallel to the cone. You can also cut it with lines, right? If you cut like exactly along the plane of the cone, you'll just get a couple of lines like x times y equals 0. So these are all, any equation that's degree 2 in 2 variables can, after some very simple manipulations, we put into one of these three types, depending on like AD minus B squared, or there's some discriminant condition that will tell you whether this is elliptic, hyperbolic, or parabolic. Okay, so we get these funny transcendental functions.
But as long as it's irreducible.
That's right. That's right. As long as it's irreducible, so this xy equals 0 would be, the union of two lines kind of thing. A degenerate hyperbola. Okay. Good. We get these funny transcendental functions, and then some funny things happen. These transcendental functions are periodic. So the sine and cosine function, of course, is periodic with period 2 pi. So really, these are functions on the circle. This is a function on R mod 2 pi z. We have this lattice 2 pi z sitting inside the reals, and we get this once periodic function, sine and cosine, that are invariant under translation. Cosh and sinh. Cosh, remember cosh? You guys know what cosh is? What is it in terms of? Perfect. Yeah, e to the t plus e to the minus t over 2. Right, that's cosh. It's just it's cosine with it instead of t. Okay, so this function, I mean, asymptotically, it looks like e to the t in either direction, right? It starts out at 1. When t is equal to 0, cosh is 1. That corresponds to x equaling 1. And then it grows exponentially in both directions, right? It's always at least 1, and it's even. So this is the cosh function. Is this periodic? Ah ha ha, it's complex analysis. It is not periodic in the reals, but there's nothing stopping us from studying both the sine and the cosine function and the cosh and the sinh function over the complex numbers. So over C, only when you go to the complex variables, do you pick up a periodicity. It's periodic. Cosh of t is the same as cosh of t plus 2 pi I. If I shift by 2 pi I, both of the exponentials don't change. Okay, so over the complex numbers, it also is invariant, but it's invariant now over a lattice. You see, what's this lattice, 2 pi z? Inside the reals, that's 2 pi, 4 pi, negative 2 pi, negative 4 pi. This is the lattice. We can call that lattice lambda, 2 pi z. But as I said, there's no reason to study this over the reals. You can study over the complexes. Modulo translation, now we have the whole group, translation by 2 pi. So we have these cylinder fundamental regions, these tiles are these infinite cylinders that will tile the plane. And once you know what's happening in one cylinder, you know what's happening everywhere because the function has this periodicity. The cosh function does not have any visible symmetries over the reals. But when you go to the complex numbers, it again has exactly the same visible symmetries, except with the lattice 2 pi I z. So once you know what happens to one horizontal strip of cosh, you know what's happening everywhere because it's just the same. Okay, so we know how to parametrize ellipses and hyperbolas and parabolas. Those parametrizations involve transcendental functions. And those transcendental functions, not necessarily over the reals, but over the complex numbers, become periodic. It turns out, and I want to explain the story of how that comes about. If you look at elliptic, these things called elliptic curves, again, having nothing to do with, at least in terms of their shape, over the reals, right? This is the curve over the reals. In terms of the real shape, this again has nothing to do with, this again has a parametrization. I want to understand how to parametrize these things, and that parametrization. So let me write these down. We want a parametrization of this curve, and that parametrization, it turns out, will have a periodicity and hidden symmetries. Just like cosh had a hidden symmetry, right? It's not symmetric on the reals, but extended to the complexes, it has the symmetry. It has hidden symmetries. Does anybody know what kind of periodicity we will have? It'll be doubly periodic, in fact. Not just a single translation, but translation in two independent variables. Okay, that's the hidden symmetry. These things will be doubly periodic. Doubly periodic. So what most modern treatments just say, there's these things called elliptic curves. Here's what they look like. Never mind why the word ellipse is there. And really what we want to study is doubly periodic functions on the complex plane. And then we just jump right in. But actually there's a beautiful story. I see why they skip this story, but I actually like this story a lot. So I want to explain to you how this came about and what happened. All right. Any questions so far? Can you guys see can you see what I'm writing? And it's okay. All right. So before we get to elliptic curves, we have to get to elliptic functions and elliptic integrals. So elliptic integrals are easy to explain. So let's try to work out, this is the kind of thing that happened, 1670s or so. Let's go back to I'll just call it 1650s. And Newton, what is Newton doing around this time? Parabolas? Gravity, yes, exactly, gravity, thank you, beautiful. His theory of gravity, right, this inverse square law of gravity that he observes, the famous apple falling on his head, and he sees the moon. That's what people don't remember. It's the moon that's important. He thinks the moon is falling towards Earth in the same exact way as the apple is falling towards Earth, for the same reason. And if that's the case, if there's this if there's these universality of the laws of gravitation, then if the moon is actually moving really, really fast this way, while it's trying to fall towards the Earth, it'll just continue falling towards the Earth, but never quite getting there if it's going too fast. He understood what satellites were for the first time. And he, this inverse square law, which already Galileo had, suggested in some primordial sense. You could, if you're very, very generous, you could say, you can see hints of it in Galileo's work. But he gets this inverse square law, and what's the first thing he proves with the inverse square law? Robbie.
Kepler's.
Exactly. Kepler's laws. So Kepler observes empirically that it looks like things aren't moving, that the planets aren't moving around the sun by circles, but there's a deviation from that circular orbit. And he calculates that deviation and sees that it's an ellipse. And Newton rigorously proves that he solves the two-body problem. Mathematicians are still trying to solve two-body problems all the time for themselves. Hello, please. What did I do? Did I upset you? I upset the gods of... Did I touch something? Oh, this is going to be bad. If I can't use the tablet, I'm not going to be able to write. What did I do? Nothing. I can still write. Where's my tablet? Please. There it is. Ah, there we go. Okay, I'm going to leave that open. As you can see, I haven't done this in a while, so working out all the kinks again. Right. So his inverse square law implies Kepler's law, implies Kepler that if you have a sun and a planet moving around the sun, it moves about it in an ellipse. So the two-body problem is solved. Elliptical orbits, ellipse. Elliptical. I can't leave it ellipse orbits. Elliptical orbits. Okay. So the very first thing you might want to know is, how far is the Earth actually traveling over a given period of time? How far does a body travel? How far does the Earth, say, travel over time? Well, that's very simple. That's just, what? How would you compute this kind of thing?
Parameterize the path and then integrate.
Yeah, it's the arc length, right? Let's parameterize the path and integrate. So, i.e., what is the arc length? What is the arc length of an ellipse? Well, let's try to work this out. So how about a simpler case? So simpler is, let's first work out the arc length of a circle. Circle. So here's my circle. X squared plus y squared is equal to 1. Let's use y as our variable. So I'll solve for x. So x is equal to square root of 1 minus y squared. Now for any curve, how do you find arc length? What is the arc length, let's say, of some curve? What do I integrate? I integrate the arc length element, where what is the arc length element? Exactly. It's just the Pythagorean theorem. Dx squared plus dy squared. So I want to know a little change along the arc is whatever it is. It's a little change in the x direction and a little change in the y direction. And the Pythagorean theorem tells me that that's how I get a little bit of arc length. Okay, so we want to integrate ds, where ds squared is dx squared plus dy squared, just the Pythagorean theorem. Okay, so let's work out what that is. So I'm going to implicitly differentiate both sides of this. So dx is equal to, what's the derivative of this thing? Hopefully you all know. The 1/2 comes down, 1 minus y squared to the minus 1/2, chain rule, minus 2y dy. Did I do something wrong? Yeah, we're doing Newton calculus right now. Don't worry about epsilons and deltas. We just want to race and get somewhere. Right? This is a historical. This is exactly how they would think about these things. Isn't this how you did it in Calc 1? You know too much now. You're like, wait, none of this is kosher. Yeah, you're right, but let's get to the answer. Okay, so I want dx squared. So let's square everything. So dx squared, the 2's cancel, the minus sign I don't care about. That's a y. So I get a y squared on top. I get a dy squared. And on the bottom, I get 1 minus y squared. Does everybody get that for their calculation? Okay, so if I want the arc length, so let's see. Let's say we go from y equals 0. This is why I like y. Y equals 0 up to some y naught. Let's say we have some y naught. So the length of the arc, of this bit of arc, will be an integral from 0 to y naught. Why not? Because, stupid joke, I don't know. Yeah, so we didn't finish the calculation. What is ds squared? So I want to add y squared over 1 minus y squared dy squared to y squared. Okay, so I'm replacing x, I'm substituting dx squared in for this. And so what do I get? I add a 1 minus y squared over 1 minus y squared. I'm writing this as 1 minus y squared over 1 minus y squared. And so I have 1 minus y squared plus y squared. That's just a 1. So I get a dy squared over 1 minus y squared. Very good. And so that's ds squared. So ds is dy over square root of 1 minus y squared. Is everyone with me so far? I actually know the antiderivative of 1 over 1 minus y squared. Almost arc sine. Yeah, it turns out it's arc sine. Yeah. So this thing has an antiderivative, and it's arc sine. By the way, that's why it's called arc sine. It's the arc length. If you know what the sine is, it'll tell you what the arc length is along that. Okay, and it's arc sine of, well, y naught minus 0, but arc sine of 0 is 0. So it's just arc sine of y0. Wait a second. There's a much, much, much easier way to do this calculation. If we know this angle, if theta is the angle, let's call it theta 0, then sine of theta 0 is equal to y0. And arc sine of y0 is arc sine of theta 0. So that's just theta 0. Of course, the arc length is, that's the whole point of using radians. Radians, you go around the angle goes around 2 pi, the circumference goes around 2 pi of a unit circle. Right? So actually, so this thing is what we will see as an elliptic integral in a second. This is a baby case of an elliptic integral because we can evaluate it explicitly. And this is the inverse of an elliptic integral. And that's called an elliptic function. Elliptic function is an inverse of an elliptic integral. And it's this thing that has periodicity. Okay. How much, so that was for the circle. How much of this would change if we did an ellipse instead of a circle? Can I get a green? Thank you. So if we had an ellipse instead of a, let's change this to an ellipse. How hard could this be, right? We're going to get the same kind of shape. What do you think? Is this something is this a good quiz problem? Or let's work this one out together. Oh, there was one more thing I wanted to do before we go to the ellipse. Let's make one more little change of variables. Because I think it'll be useful for the other thing that I want to do. So another way to see this theta zero, another viewpoint on this. Let's change the polar coordinates. In polar coordinates, what does this look like in polar coordinates? Polar coordinates. So in other words, how do I parameterize x and y? What's the change of variables from rectangular to polar? You guys remember this? R cosine theta, R sine theta. Exactly. R cosine theta, R sine theta. And so if I differentiate both sides, dx is, now I have both r and theta are changing. So I get a product rule. So I get a dr times cosine theta minus sine theta times r times d theta. Right? I'm leaving the r alone, differentiating cosine implicitly. And then same thing with y is dr sine theta, now r plus cosine d theta. Okay, so what is dx squared plus dy squared? Okay, the x squared, this isn't so hard. I get a dr squared cosine squared. Let's do a plus r squared sine squared d theta squared. And then what's the cross term? It's a minus 2 r cosine theta sine theta dr d theta. That's just squaring x. Did everybody get that? Am I doing this too fast? No. Okay. Or too slow, maybe. How about dy squared? You guys all know what it's going to come out to. Does everyone know what it's going to come out to? Okay, not everyone knows what it's going to come out to, so let's do it. Sine squared. You probably, I'm sure, did this as a kid. Okay, the squaring this is a r squared cos squared d theta squared. And then now what's the cross term? It's a plus 2r sine theta cosine theta dr d theta. So that's nice. Those cancel. Oh, this is nice too. What does this all add up to? dr squared r squared d theta. Okay, maybe that rings a bell, that this is the arc length. Okay, so if we were to do this in polar coordinates, what's the equation of a circle in polar coordinates?
R equals some constant.
R equals 1. Yeah, some constant. Yeah, let's say the unit circle. R equals 1. That's the equation of a circle. R equals 1, regardless of the theta. So if I implicitly differentiate this, dr is equal to 0. And so if I want to integrate ds, that is, so ds, so what is ds? Now dr is 0 and r is 1. So ds squared is just d theta squared. So ds is d theta. So it's an integral from 0 to theta 0, theta naught, of d theta, which is just theta 0. Okay, so that's another way of seeing exactly this calculation. It's a very, very complicated thing, but actually I'm going to use this in a minute, so I want to keep it here. Just confirming our calculation here that the arc length is just the angle. Okay. How much of this changes? Again, is this a good thing to give you as a quiz? Let's do this together, and then the next one I'll give you as a quiz. How much of this changes when we make it an ellipse? This can't possibly change that much, right? What's the difference between a circle and an ellipse? It's like the same thing. Let's see. Okay, so I want to solve for x. I move the y to the other side, but now I have to multiply by k squared, and I'm taking square roots, so I get a k here. Everybody agree with that? When I differentiate, well, that k is just a constant. Okay, so when I solve for dx squared, I just get this k squared there. I plug that in here, and here's where things get funny. I add a 1 minus y squared to a k squared y squared. And the y squared minus y squared and plus y squared no longer cancel. So I get an extra factor of 1 minus, I guess a 1 plus, I get a factor of k squared y squared here and a minus 1 y squared there. Can you guys see that? So when k, notice when k is equal to 1, this term isn't there. Okay, so then when I want to integrate, I take the square root of that. So I want to integrate the dy over 1 minus y squared with a factor of 1 plus some constant. Well, I'll leave the constant k squared minus 1 just to not make things too complicated, y squared. And they got stuck. Actually, Newton didn't get stuck at all. What did Newton do? If you're Newton, what do you do? What's his favorite theorem at this point? The binomial. Newton's binomial theorem is how to expand these kinds of things into series. He just expands everything in the series, integrates term by term. He can work out as many coefficients as he wants. No problem. He has, to whatever precision he wants, he understands this function. Of course, if you do that, you won't see the things to come. It's very hard to invert functions that you are given by a series expansion. Okay, so if you're Newton, you're perfectly fine with this. You expand in series, you can calculate to your heart's content. What else could you want in life? But later authors come to this and they go, no, really, what is this? It's a new class of functions. They're transcendental functions. There's no nice antiderivative any longer. But Legendre spends the next, we're already up into, so Euler, Legendre, these guys start doing these calculations again and again and again, and they keep seeing the same kinds of funny functions occurring, and they can reduce all of their arc length calculations down to certain classes of functions. So let's do one more calculation from scratch and see where it takes us. Okay, so one more example before we see the general theory. So one more example is the lemniscate. R squared equals cosine of 2 theta. This is a very, there are a lot of reasons why people studied this thing. So what does this look like? Let's try to get a graph of this. Well, I gave it away. You've seen these kinds of things in polar coordinates, right? If theta is 0, what's cosine of 0? 1. So R is 1 or negative 1, right? It's going to be, so R is 1. Well, R can't be negative 1. So let's leave R equals 1. R is positive, right? Although you'll see in a second. Okay, and as theta starts increasing, as the angle starts increasing, as I start coming up, what's happening to cosine? It's decreasing, so R is going to get a little smaller. So as the angle starts coming up, R is going to start getting a little smaller. We're going to get closer to the origin. Where does cosine hit 0? At pi over 2. So cosine of 2 theta will get there at pi over 4. So at pi over 4, when we're at a 45-degree angle, we're coming in to R equals 0. And we're going to go right through that. And now we have this kind of figure 8 lemniscate situation that's supposed to be through the origin. Lim, L-I-M, lemniscate. Lemniscate or lemniscate? Can anyone Google, save me from embarrassment? I'm sure I wrote it down somewhere. Anyway. N-I. Lemniscate. Thank you. All right. What if we were to try to write this out in, maybe that's a good quiz. Write this in X and Y's. Convert to X and Y. I'll give you a hint. Cosine of 2 theta is cosine squared theta minus sine squared theta. Yes, please. Yes. Yes. So, yeah, you have to reinterpret this allowing negative r's. That's one way of thinking about it. Yeah, that is true. That is very true. So even better to convert it into x's and y's and interpret it that way. This will agree in the range where both of these are interpretable. The x and y version will give us the full curve. Sorry? This, yeah, cosine of 2 theta, I'm just reminding you, the cosine of 2 theta is cos squared minus sine squared. So, yeah, why not? The question is to convert this equation into x's and y's. Just something to, you know, keep the kids off the streets. Right, so r squared is easy. That's x squared plus y squared. We haven't done anything yet. Oh, no, I'm just reminding. Yeah, okay, I shouldn't remind you of anything. You're right. You're right. Take your time. Take your time. Let you think about it. This shouldn't be, this is like Calc 1 kind of stuff. So I'll just remind you that x, we already said was r cos theta. But what is cos theta? So if I have some, I want to know if I have some point, this distance is x, so what's the angle? This distance is square root of x squared plus y squared. So the cosine is x over square root of x squared plus y squared. That's all I'm going to remind you of. Because that could be something that takes you a second to think, like, what am I supposed to do with this? Also gives me an opportunity to one more. You, and I'll trade you. Should we do it together? So what is the cosine squared minus sine squared? Uh-huh. Exactly. And r squared. Great. So you can multiply through by x squared plus y squared if you like. And equivalently, x squared minus y squared is equal to x squared plus y squared squared. Okay, so maybe that's a better way of thinking about this than thinking about what happens to square roots of negatives or. But That's true. That's true. So that means that y squared will never be greater than x squared. So the whole thing's going to live inside this pair of 45s. Okay, does that make sense? You'll see in a second, we do not want to implicitly differentiate this and solve for things. This is much, much more convenient to work with. So let's work out a bit of arc length. Let's work out a bit of arc length. Actually, that's what I had in mind to give you as the quiz. Do you want to do a little more calculation? You feel like it? In the mood? Yeah, let's do it just a little bit more. Okay, so let me remind you that ds squared is equal to dr squared plus r d theta squared. Let's implicitly differentiate both sides of this and try to simplify this. Let's say in terms of r. So we'll think of this as r going from 0 to whatever the radius is out here, whatever this distance is, r0. So the length will be an integral over ds, which will be an integral from 0 to r0 in r. I'll try to work that out. Yes, as r goes from 0 to some, right, as the radius gets larger and larger, we get more, we get these points along the curve. So we're parametrizing, we want to think of the curve in terms of r in this positive direction. So theta will start at like pi over 4 or something and move down to 0. We just want to understand that little bit of arc length. You've made progress. Did you implicitly differentiate this successfully? Yes, Eric.
When we write like dr squared on the left hand side.
Exactly, 2r dr
Oh, okay.
is that bit. And then let's differentiate this. What'd you guys get? Negative sine of 2 theta, chain rule 2 and d theta. So we can cancel the 2's on both sides, and we'll square both sides. So we get r squared dr squared is equal to sine of 2 theta squared d theta squared. Okay, I'll let you continue from there. We want to solve for d theta. So this sine squared we want to turn into r's. But sine squared is what can you do with sine squared? You know what r is in terms of cosine. Yeah, so sine squared is 1 minus cosine squared. Well, cosine is r squared. So cosine squared is perfect. Yeah, they're both of 2 theta. So if we solve for d theta squared and plug that in over here, we should get something reasonable. So what'd you guys get?
One plus r cubed equal 1 minus r squared.
Almost. If I solve for d theta squared, so in other words, I'm going to divide both sides by 1. Let me just do it. I'm going to divide both sides by 1 minus r to the 4th. Well, that's, I'm dividing by this. So that's what d theta squared is. That's why you said r cubed, because I wrote this incorrectly. Sine squared of 2 theta is equal to.
From what we have before, it's cosine squared minus r squared, right?
No, sine squared is 1 minus cosine squared, just always.
Oh, I see. Okay.
And the cosine is r squared, so cosine squared is r to the 4.
Yeah.
And so if I move that r to the 4 down, sorry, I copied this down wrong. It's r squared, it's dr squared plus r squared d theta squared.
Oh,
That's why you were getting a cube. What is it, kids? Let's see. So I'll stick this in for d theta. So I get an r to the 4th here. And this thing is just 1 minus r to the 4th over 1 minus r to the 4th. If I put them over a common denominator. So I'll put a 1 minus r to the 4th over 1 minus r to the 4th. So I have a 1 minus r to the 4th and then a plus r to the 4th. So I just get a 1. Is that what you were saying? We're going to, we're going to integrate that. So that's ds squared. So we're going to integrate dr over the square root of 1 minus r to the 4th. That's another kind of integral that became known as an elliptic integral. Okay? So this is another elliptic integral. Starting with the difficulty of ellipses, now you do lemniscates, now you do all these other lemniscates, not lamniscates. Now you do all kinds of other things. And Legendre got this down to, like, really made this into a science. He spent 40 years developing all the different kinds of things that could come up. And he came up with these 3 kinds of functions. First kind is usually called Legendre F function. It is an integral from 0 to u of d, let's say dx, over the square root of 1 minus x squared times 1 minus some constant x squared. Okay, that's the first kind of integral. Do we have we seen this kind? Oh, actually, we haven't seen this kind yet. A second kind is called the E function, traditionally. None of this is very important for you to know, just for your general knowledge, is 1 minus k squared x squared over the same thing, 1 minus x squared times 1 minus k squared x squared dx. Have we seen this function? Exactly, right? What is it? We have a square root of 1 minus k squared x squared on the bottom and just a factor of 1 minus k squared x squared on top. That's the same thing as having the square root in the top. And that is exactly, when we were working out the ellipse, what we saw in the ellipse. There was a 1 minus y squared and then a 1 with another constant y squared on top. So this thing is a type 2, is of the second kind. So this is where the ellipse, this is, for example, the actual arc length of the ellipse, which is where the term elliptic integral comes from. And the last one, the third kind, let's see, did I do something wrong? I think there's a plus here. Anyway, it doesn't matter what these are. If there's a plus here, let's say there's a plus here, then do we recognize this? With k equals 1? That's what we just did. 1 minus r squared factors as 1 minus 1 minus r to the fourth factors is 1 minus r squared times 1 plus r squared. Okay, so the first kind should be this lemniscate. Lemniscate. Okay, so that's the first kind, second kind, and then there's a third kind. Doesn't really matter. Goes by capital pi. I'll write it down just for completeness, but there's no reason to remember these things. I don't remember these things. 1 plus nx squared times the same kind of 1 minus x squared times 1 minus k squared x squared. Something like this. Don't quote me on any of this. It's not so important what these are. He spent 40 years working all of these things out. And this is like 17, I'm just going to put a random number, 1780s. And made a big theory of this. Like, if you know, using these three functions, there was like a whole class of arc length type integrals that he could evaluate in turn, that he could reduce to these. Okay. And then it's not until Abel and independently Jacobi, although Gauss had these ideas, he just didn't tell anybody, that thought, wait a second, the important thing isn't the elliptic integral, it's the elliptic function, which is the inverse function, the inverse function. So they want to replace elliptic integral. Elliptic integrals are out. Elliptic integrals are out, and they're replaced by long-lived elliptic functions. Elliptic functions, which is the inverse of elliptic integrals. Okay, so let's think about why that even exists. Let's think about this function, for example. The map example, the map R gets sent to the integral, I should call it a dummy variable, the integral from 0 to R of dx over square root of 1 minus x to the 4. Okay, should we give this function a name? Well, it already has a name, capital F. Fine, so this is capital F. It's a special case of capital F. So what is the derivative of capital F? Let's try to get a graph of capital F. So here's capital F as a function of R. When R is equal to 0, the arc length is 0. We haven't gone anywhere yet. We're still on this part of the lemniscate, and we're going to start moving up and start gaining in arc length. So what's the derivative? Fundamental theorem. Yeah, thank you, Dana. 1 over square root of 1 minus r to the fourth. Now notice when R is going to have a problem once it gets to 1. We're never going to get past 1 on this arc length graph, but that's okay, at least for now. What is happening to this thing? This square root of 1 minus r squared. What's the derivative when r is equal to 0? 1, exactly. So derivative of 1 is 45-degree line locally. How about when r is getting closer and closer to 1? What's the derivative? As r approaches 1 from below, Dana, infinity. Okay, so as we go to, but it's going to have a finite limit. It's just going to do something funny. It's going to go like that. There's a finite limit here, which is the total length of that lemniscate up to that first little lobe of the ear, right to there is r equals 1. Okay, so whatever that value is, let's call it, I don't know, alpha or something. Whatever, it doesn't matter what it is. Okay, so this is the function f. Now I haven't drawn it very well. Well, it's not so bad. Or maybe it just goes more straight than when I've drawn it. Anyway, whatever it's doing, this is probably not a great picture of what it's doing. Whatever it's doing, this derivative is positive. So it's strictly increasing. Which means it's 1 to 1, which means it has an inverse. It has an inverse. So the inverse function, Jacobi called it the sin function. This is the sine amplitude function. He called it the sine amplitude, again, for complicated reasons, function. Okay, so if we call this R and we call this, I don't know, how about L for length? And so if L is equal to F of R, then sin of L is equal to R. So that's this inverse function, which is just you take the original and you flip it over the y-axis. The x equals, not the y-axis, the x equals y 45-degree line, right? So that's this inverse function. And these functions are easy to understand because you know the derivative. What's the derivative of Sn? How do we work out the derivative? You guys remember this? So what's Sn of f of r? Sn's the inverse function, so it's just r, right? Doesn't do anything. So if I differentiate both sides with respect to r, this is all Calc 1. I'm just reminding you Calc 1 again and again. Let's differentiate both sides with respect to r, ddr of that. Derivative of Sn is whatever it is at f of r times chain rule f prime of r. On the other side, I get 1. Oh, right, of course. The derivative of an inverse sign is just 1 over. So the derivative, now I'll replace f of r by L, is equal to 1 over f prime of r. R is Sn of L. But I know what f prime is. F prime is 1 over square root of 1 minus r to the 4th. And so 1 over that is just the square root of 1 minus r to the 4th, where r is Sn of L. Ooh, we get this nasty differential equation, Sn prime squared. So we get this differential equation, Sn prime squared is equal to 1 minus Sn to the 4th. All right, whatever it is, you know, in these days, people are perfectly happy solving these kinds of differential equations. But it's from these kinds of differential equations that Jacobi in particular found this double periodicity. Double periodicity. Double periodicity. What is double periodicity? So now I think I've given you enough of a crash course in what happened. None of this stuff is going to be relevant to what we want to do. But now we want to study doubly periodic functions on the complex numbers. And this is where they came from these. And I think Stein-Chikarchi have this great quote. Let's see if I can find it. They have this great quote. Page. How do I get to page? Why can't I move? There we go. Now you'll understand the quote. Come on. Why can't I just go back? I have to do this. It's going to be painful.
There's like a little
Slider. There we go. Okay, applications of theta functions. Oh wait, that was it. Come on. Theta functions. Yes. Okay. Here's Poincaré. Now, Jacobi and Abel are like 1830s, right? These are both guys that died young and so on. The form that Jacobi had given to the theory of elliptic functions was far from perfection. Its flaws are obvious. Of course, you have to understand what it is to understand its flaws. So it turns out that he had this sine amplitude, he had another Cn, and he had a Dn, which were the inverses to those other. Well, Cn is actually square root of 1 minus Sn squared to mimic sines and cosines. It was a very, very convoluted thing, and it was very difficult to work with. So that's why when Poincaré, 70 years later, is saying its flaws are obvious, well, you have to understand what it is to know why its flaws are obvious. At base, we find 3 fundamental functions, Sn, Cn, and Dn, exactly as we discussed. These functions do not even have the same periods. They are doubly periodic, but their periods are different. And Weierstrass comes up with a system instead of 3 fundamental functions. There's only one, the Weierstrass P, which we will discuss in detail. And it's the simplest of all and has all the same periods. It has one double at infinity, which we'll talk about in a second. And anyway, so I wanted to explain this paragraph because as anyone else, he jumps straight into, let's talk about doubly periodic functions, which are called elliptic functions. Okay, so elliptic integrals, I should say, the more general setting, if you look at all of our examples, more generally, the more modern viewpoint is that any integral of the form something about t and something about the square root of a polynomial in T, and that something is a rational function. So this is a rational function. In other words, ratio of polynomials, rational function. And this is like a cubic, a quartic, let's say degree at most four polynomial. So it's a rational function in T and in the square root of a degree at most four polynomial. That became known as an elliptic integral. This is what, when someone says elliptic integral today, this is what they mean. And if you notice, all the ones that we have seen are rational functions, like, you know, square root of 1 minus k squared over t squared over square root of 1 minus t squared or whatever. It's a rational function, it's a polynomial involving potentially square roots of 1 minus t squared or 1 over 1 minus t to the fourth, right? They're all of this form. So this became known as the general elliptic integral. And people tried to understand these. So that's what Stein-Chakarchi are saying here, right here. I don't know why it won't highlight. Okay, forget you. I don't want to highlight you either. And again, more generally, elliptic functions became synonymous with, people forgot all of the stuff that we talked about. It became synonymous with double periodicity. That's it. Doubly periodic functions. Doubly periodic, holomorphic, or meromorphic functions on, I don't know what just happened. C. I pressed something. Okay, so let's talk about double periodicity. So far, so good. I wanted to explain that paragraph. Nobody does it anymore. Everyone's like, as we all know, this is what happened, and these old-fashioned people were doing this crazy stuff. We don't care about that anymore. Here's the modern theory that leads to all kinds of beautiful stuff. I think it's still important to look over what the old man, you know, Abel was not that dumb a guy. Jacobi, Gauss. These people were doing things that I still today find interesting. All right. So again, let's look back over where we started. There are ways of, so we haven't gotten to the parametrization and we haven't gotten to the elliptic curve. That will all come from Weierstrass's theory. But at the very least, we have seen that studying arc lengths of things like ellipses, in particular circles, gives us functions whose inverses have nice periodicity. And sines and cosines have real periodicity, and coches and sinches have complex periodicity, but again, only single periodicity. There's a lattice generated by a single translation, whether sideways or up and down, that's responsible for that. Let's try to understand what happens to doubly periodic functions, which of course you can't have in the reals. You can only have double periodicity if you have another direction in which to move. And by the way, there's at most doubly periodic functions, because you can't be thrice periodic without being either dense or just being doubly periodic in some other lattice. Okay, so what does it mean to be doubly periodic? Doubly periodic, so F is doubly periodic if what? F of z plus omega 1, omega is 1 period, is equal to F of z for all z. So if there exists some W1, that's singly periodic, like W1, omega 1 could be 2 pi or 2 pi I. And there also exists a W2, so that this is F of z plus W2. Now, if W1 and W2 are in the same direction, so let's think about F of 0. So this is 0. W1 is, I don't know where W1 is, here. Now, if W1 over W2 is real, then they're pointing in the same direction. Like W2 would be over here some, or over here. And then double periodicity is just single periodicity. And if this number is rational, then it's actual periodicity. And if it's irrational, then it's just all over the place. So we don't want this. It's not real double periodicity. Eric.
But if omega 1 and omega 2 are real, but it's like irrational or something, then does that mean that function is just constant on that line?
Yeah. On all lines in that direction. Yeah, then it's not, it's even worse. Yeah. But as long as we get away from that setting, now what as long as, so assume that W1 over W2 is not real, then they're genuinely pointed in some other direction. I don't know where to drop W2, over here somewhere. This is W2. There's W1, there's W2. And then it doesn't matter what real or there's no issues about the quotient being real or rational or anything else, because whatever value f takes here, it takes exactly the same value here, which means it also takes exactly the same value at 2W1. It also takes the same value at W1 plus W2. It also takes the same value at here and here and here. So if we start drawing these lines, these parallel lines, and these parallel lines, we see that space has been cut, the plane has been cut into tiles by this fundamental tile, this fundamental domain. So this fundamental domain is the term tiles the complex plane. And if we know what the function's doing in that one tile, we know what it's doing everywhere because of the periodicity. Okay, so this fundamental domain tiles, and the fact that it's invariant under omega-1 and omega-2 means it's actually a function. So f is not a function just from the complexes to the complexes. It's actually a function on the quotient of the complex plane by the lattice generated by, this is the lattice generated by W1 and W2. In other words, all integer multiples of W1 plus integer multiples of W2. Okay, so this is a lattice in C, rank 2 lattice, abelian lattice in C. And f is really a function on this quotient. Does that make sense? Okay, well, because if you had a rank 1 lattice, the original thing was just a rank 1 lattice, like 2 pi z is a rank 1 lattice in the complex plane. But this is actually genuine rank 2, in other words, doubly periodic, genuine double periodicity. Now, what is this quotient? When we thought about the sine function is a complex valued function, is really a function on a cylinder, because it's only periodic in z goes to z mod 2 pi. With these two ends we can identify, but then we have this infinite cylinder. It's a torus. This quotient is a torus because this side is exactly identified with that side, and similarly this side is exactly identified with that side. Okay, so these doubly periodic functions are really functions on tori. This is a torus. Right? You guys have seen this. You take a cylinder, fold it up, and then fold two ends of the cylinder, so it looks like a donut. Okay, so this is a Riemann surface. Another instance of that. Okay, very good. What can I say in 9 minutes about this? Quite a lot, actually. There's very, very low-hanging fruit here. The second you start thinking about functions like this, all kinds of magical things happen. Okay, how can we, does any such function exist? Does any such non-constant, okay, the constant function, of course, is invariant under translation. Non-constant function exist? Let's try a holomorphic function. How about f is holomorphic? Tim says no. Why? Yes. It would be bounded because whatever it does on this compact tile, it does everywhere. So immediately, holomorphic functions are out. Okay, holomorphic would be entire and bounded. Liouville tells us they're constant. Okay, so we cannot have holomorphic functions. We have to have some, at least some explosion. And by the way, this is what Poincaré says. It has only one double infinity. So I'm going to come back to that. This entire lecture is going to be explaining this opening paragraph of Poincaré. So how, okay, so fine. It can't be holomorphic, but how do we make a function that's invariant under a lattice. There's a simple, anytime you have a group action, you can try to make something invariant under that group action by yeah, let's say I want something invariant under the icosahedron. So I put some function, any function whatsoever on the icosahedron, and now I want to make out of that a function that's invariant under the icosahedron. Well, why don't I just add up all the possible symmetries? And when I add up all the symmetries, the function will be invariant under the symmetries because I added them all. Right? So try averaging, try what number theorists call averaging, as you'll see in a second. I don't like this word, but it's way too late to change it. Try averaging over the group, over the group of symmetries. In other words, let's make an F by taking some auxiliary function G and moving it by lambda and summing that over all lambda in lambda. In other words, just take any function G, some nice smooth function potentially. It'll have to have lots of decay, obviously. So G will have to have decay, and we will sum over all the lattice points, all the lambda in the lattice, and translate G by lambda. And this will be a function as long as this converges, as long as this converges absolutely, it will be f of z plus lambda will be f of z, because if I replace z by some, plus lambda 0 for some fixed lambda, I just make a change of variables. This is a group. I just make some change of variables, and you're shifting around where we're still summing over the same thing. Okay. How do we make this converge? What's a typical element lambda? Lambda, a typical element is like W1n plus W2m, right? The lattice lambda is generated by W1 and W2, where n and m are integers. W1 and W2 are fixed. We're saying, suppose these are the periods. Kind of like, suppose we have the eccentricity of the ellipse. The k wasn't even a parameter. It's just fixed for all from the beginning. So this W1, W2 we think of as being fixed. How much decay do we need? So suppose G of Z has decay like some constant over, let's say 1 plus Z to, I don't know, alpha. Suppose it decays like Z to a power. How much decay do we actually need in order for this to converge absolutely? Let's work that out. I'm not saying it should be clear, or is it already clear? What conditions on alpha? The question is, what conditions on alpha guarantee absolute convergence? Andrew? Yes, exactly. The answer is alpha should be greater than 2. Maybe that's not obvious to everyone, so let's just do it. It is a rank 2 lattice. So one way I like to think about this is if you think about the lattice, wherever it is, we have this rank 2 lattice, right, lambda. If we think about any fixed radius r, how many lattice points are there between r and r plus 1? So the number of elements lambda in lambda, with the absolute value of lambda being between, let's say, r and r plus 1. Just completely trivially, I want some simple upper bound in this little ellipse. Not ellipse, what's it called? Annulus. So in this annulus, how many possible lattice points will we see? Well, the lattice points are all have some spacing between them, right? There's some fixed amount of space that no lattice point gets within that distance to its neighbor. And so any 2 lattice points here have to differ by at least that space. And so a crude upper bound for how many there could be up to constants, I don't care about constants, is just the circumference of this circle. And the circumference is, 2 pi r, 2 pi r plus 1, r plus a half, doesn't matter. So 2 pi r. Okay, so crudely, the number of points that you'll get in this width 1 annulus on the lattice is at most some constant times r. Hopefully you believe that. And so now let's try to get the absolute, let's try to sum. So the sum over all translates. Z is in a compact set. I can think of Z as being 0. Z is in the fundamental tile. So think of Z as being either 0 or in some compact region. It's not going to change anything about the bound. So let's write this. This is at most a sum over, let's say a sum over R, integers R greater than or equal to, well, 0 or 1, whatever. Let's put a constant here in case R is equal to 0. R greater than 1 integers, and then a sum over all lambda lying between R and R plus 1. So I want to grade this by the annulus and having larger and larger annuli going out, and then G of lambda in absolute value. Now we just said that G is going to decay like 1 over Z to a power alpha. Okay. So this thing is bounded. There's this constant. There's R greater than 1. There's a sum over these lambdas in the annulus. G is bounded by, let's say, a constant over lambda to the alpha. But lambda is of size R. So I could call this R to the alpha. You agree with that? Okay, so there's an R to the alpha, and how many lambdas are there in this range? Oh, you can't see behind that. I thought, you know, sometimes there's these Zoom things that the people on Zoom can't see, but you're not seeing Zoom, you're seeing my screen. So you can't see. I don't know if I can move this. Oh, I can. Very good. Go away. Yeah, so how many points of lambda are there in this annulus? At most R. So this sum has size R. So when does the series R over R to the alpha, when does that series converge? Converges when alpha minus 1, this converges, the harmonic series diverges. This converges when this is the exponent alpha minus 1 is at least 1. Okay, so that's why alpha needs to be at least 2. That was this alpha is at least 2. So G, whatever G is, we can take any G as long as it decays at least like 1 over x squared and a little bit more, we'll make an elliptic function. Can anyone come up with a G that decays at least like out at infinity, at least like 1 over something squared? Yeah, 1 over 1 plus z squared just fails to do it. If you want it to be holomorphic, or at least meromorphic, right? This is going to have some poles. You can do something like this. So that's a function. In fact, any rational function, P of z over Q of z, with total degree, with degree of P being at most the degree of Q plus 2, strictly, or maybe let's be explicit, with total degree at most -3, is going to be something where the numerator over the denominator will grow like 1 over z cubed, and 1 over z cubed is plenty. So you just take your favorite rational function, average it over the group. You'll be able to average it over the group, and it'll converge. And the question became, and this is where we're going to stop, can you do, so this is cubic growth. So we easily get cubic decay at infinity. And the question is, can we get quadratic? Can we somehow regularize things so that we can get quadratic decay at infinity for this G? If I put a 1 over z squared here, it will not converge absolutely. But maybe there's something we can do to temper it.
Why does it matter?
Why does it matter? It turns out that if you can get this quadratic one, you can get all of them in terms of this one quadratic one. So that's just the last thing is it has a double infinity. The double infinity is this order event, this quadratic decay. That's the double infinity. We're out of time. That's where we'll stop for today.